welcome to the students. So, last time we had seen elementary concepts and today we are going to continue with these elementary concepts. So, what had we seen last time? We had seen what are periodic points, what are eventually periodic points. We had also looked into the stable sets of periodic points and we had also looked into the unstable sets of periodic points. Now, what are the stable sets of periodic points? We can recall that once again. So, these are basically if P is a periodic point of period n, then basically I am looking into all x for which limit as k tends to infinity f k n of x is P. So, these are the points which are forward asymptotic to P. And this is what is our stable set. We recall again what do we mean by an unstable set of periodic points. So, if you look into the unstable set of periodic points, these are basically those points, say again if my f and p is P, then I am looking into all those x for which limit as k tends to minus infinity, right, f k n of x is P. So, these are basically the points which are backward asymptotic to P. Now, with this recalling of the definitions, let us now look into the properties. So, today we will be doing the first proposition that we have in this course and that is regarding the stable set. So, what ideally do we mean by a stable set? The proposition says that the stable set of distinct periodic points are disjoint. That means, if I have P and Q to be two periodic points and if K is the period of P and N is the period of Q, then we have the stable set of P disjoint from the stable set of Q. Now, let us look into the proof of this proposition. So, ideally for a proof all we need to do is we start with contradiction. So, we start with the fact that there exists, suppose there exists an x which belongs to the stable set of P as well as the stable set of Q. Now, since x belongs to both of this, I can say that given epsilon greater than 0, there exist integers n1 and n2 such that on one hand I have f k m of x minus P. This modulus is less than epsilon for all m greater than n1, and on the other hand I have f k n of f n m of P of x minus P to be less than epsilon for all m greater than n2. Now, this is true since they both belong to the stable set of P and Q, sorry, minus Q is less than epsilon. Now, what does this tell me? So, if I take my m to be greater than say maximum of n1 and n2, then we have that mod of P minus Q, right, by triangular inequality. I am just using triangular inequality. This is P minus f of n k m x plus f of n k m x minus Q. By triangular inequality, this is less than mod of P minus f of n k m x plus mod of f of n k m x minus Q. and we know that both these quantities are less than epsilon. So, this is less than epsilon plus epsilon, which is basically my twice epsilon. I could have started with epsilon by 2, this would have been less than epsilon. So, what we find is that given any epsilon, your mod of p minus q becomes less than 2 epsilon. That means, the distance between p and q becomes arbitrary. That is what leads to contradiction, because p and q are fixed points. So, that gives us a contradiction, and this contradiction basically comes up from the fact of assuming that there exists a point in the stable set which belongs to the stable set of both p and q, and hence the stable set of p and q are disjoint. So, if we look into the stable sets are always disjoint. So, this gives a wonderful kind of characterization of the dynamics of say points on the set, that if we have a periodic point, then if we have some stable sets, then maybe we have disjoint periodic points, then the stable sets will be disjoint. Same thing can be said about the unstable sets also. So, we now go with defining something, and today our basic concentration will be for looking into f, a function mapping from an interval I to R. We are only going to look into interval maps here, where my interval can be something like a closed interval, it could be something like an open interval, or it could be R. So, we will look into maps. We will basically today we will be looking into interval maps, and we will be trying to understand the dynamics from some properties of f. Also, I want my f to be continuously differentiable. For looking into, for analyzing the dynamics of f. Now, the first thing we need is some definitions. So, we try to define some points here. So, let me say that let p be a periodic point of period n. Then we say that p is hyperbolic, right. This point p is called hyperbolic if I take fn, I take its derivative, the value of this at p is not equal to 1. So, we say that we have a hyperbolic periodic point if the period is n, and if I take fn, if I take the derivative of fn at p, then that particular modulus of that is not equal to 1. So, basically this does not lie on the unit, basically this distance is not unit. Since we are only looking into this mapping from R to R, then we just want to say that this modulus is, or basically this value is neither 1 nor minus 1. So, this is our definition of hyperbolic periodic point, and we can start with looking into some kind of examples. So, let us try to look into some example here. So, we let take the first example here, say let my fx be equal to, so I am looking into 1 by 3 times x cube minus x. All I want to see is that this f will have 3 fixed points, and the 3 fixed points here are 0. So, we have 0, 2 and minus 2 are the 3 fixed points. What happens, what is the, and since these are fixed points, that means they are period 1 points, right. We can try to look into what is the character of these periodic points or these fixed points. So, if we look into what is f prime of 0, then f prime of 0 happens to be equal to 0. Is it exactly 0? What is f prime of 0? Well, I think it is minus 1 by 3. F prime of 0 is minus 1 by 3. If we look into f prime of 2, right, f prime of 2 happens to be equal to, is it 11 by 3? And if I look into what is f prime of minus 2, again that happens to be 11 by 3. Clearly, this values are neither 1 and minus 1. So, these are hyperbolic periodic points. Basically hyperbolic fixed points. We will look into the graphical analysis, or maybe we can look into the phase portrait of this periodic point and try to understand how their behavior is. So, let us draw the phase portrait of this function. So, I am looking into this particular function. I have a fixed point at 0, I have a fixed point at 2, and I have a fixed point at minus 2. Now, what happens to this particular function? At 0 it remains 0, right. What happens to points between 0 and 2? So, if we try to look into what happens to points between 0 and 2, right, they tend to get closer to, what happens to the point 1, for example? What happens to the point 1 here? 1 is mapped to 0. If I look into minus 1, right, what happens to minus 1? Minus 1 is also mapped to 0. What happens to the rest of the points here? Say take any point between 0 and 2, we find that it is coming closer and closer to 0. Any point here comes closer and closer to 0. What happens to the point which are greater than 2? So, we find that points which are greater than 2, they basically drift away from 2. The points which are less than minus 2 also drift away from minus 2. So, if I look into this function, my function is f x equal to half of x cube minus x. We find that this is basically the phase portrait of this function. Now, it is very easy to see if I want to look into what are the stable sets here. So, what are the stable sets? So, the stable sets is, what is the stable set of 0? So, we find that the stable set of 0 here happens to be the interval minus 2, 2. Interesting. What is the stable set of 2? We find that the stable set of 2 is nothing but singleton 2, right, it is just singleton 2. And the stable set of minus 2 similarly is just the singleton minus 2. Now, we would be interested in knowing what are the unstable sets of 2 and minus 2. So, if we try to look into what is the unstable set of 2, we are looking into those points which are drifting away from 2, right. So, those points which are drifting away from 2, or basically they are tending towards 2 in the negative direction, right. So, these are basically the points 0 to union to infinity. So, the unstable set of 2 happens to be a union of 2 disjoint intervals, right, 0 to and to infinity. Similarly, if I want to look into what is the unstable set of minus 2, right, the points drifting away from minus 2, and that turns out to be this interval minus 2, 0, right, union minus infinity minus 2. So, this is basically the unstable set of minus 2. We will try to look into yet another example. I hope this is clear to all of you. So, let us look into another example here, and this example is just, I am just having the same function here, but with a negative sign. So, this is minus 1 by 3 x cube minus x. Now, what can we say about this particular function? Certainly 0 happens to be a fixed point here. Is there any other fixed point here? 0 is the only fixed point here, and what we find here is that 2 and minus 2, they form a periodic orbit of period 2, right, because 2 is mapping to minus 2, right, and minus 2 is mapping to 2. It is just the previous case. In the previous case we did not have the minus sign, so 2 and minus 2 were fixed points, but here we have a negative sign, right. So, 2 is mapping to minus 2 and minus 2 is mapping to 2. So, here we have 0 is a fixed point, and 2 minus 2 are periodic points of period 2. What can we say about, now interesting fact here is that I should have this 0, right. We know that your f prime of 0 here will be 1 by 3, right. So, again 0 happens to be a hyperbolic. So, 0 is hyperbolic. So, it is a hyperbolic fixed points. Now, we are interested in what happens to 2 and minus 2. So, if we try to look into what is f square prime, right, of x, what is that turning out to be, and we find that at the point, not at the point x, instead we can just look into what happens at the point 2 and minus 2. All we are looking into is we are looking into chain rule here, right. So, at the point, let me say that what happens at the point 2, right. So, this becomes nothing but this becomes what is f prime at the point minus 2. So, this is f prime at f x. So, this is f prime at minus 2 into f prime at 2. And what is the value over here? So, we know that f prime at minus 2, so similar calculation, right. What we will get here is say minus 11 by 3, right, minus 11 by 3. The other one is also minus 11 by 3. So, what we get here is 121 by 9. So, f prime f square prime at 2 happens to be 121 by 9, which is certainly not equal to 1, and similarly this also has the same value f prime at minus 2, this also has the same value 121 by 9. So, 2 and minus 2 are hyperbolic periodic points of period 2. We can think of drawing a phase portrait here to understand the dynamics of this particular function, and the phase portrait here is simpler. It is different than the previous case, but again my 0 remains fixed as it is. If I look into my 2, right, my 2 and minus 2, they form a periodic orbit of period 2. So, what I have here is I have 2 being mapped to minus 2 and I have minus 2 being mapped to 2. What happens to 1 and minus 1 here? So, if you look into 1 and if you look into what happens to minus 1 here, then 1 and minus 1 under this map, they both map to 0. So, 1 is mapped to 0, minus 1 is mapped to 0, these both are mapped into 0. What happens to a typical point between 0 and 2 here? So, if you look into any point between 0 and 2, it basically gets mapped to something smaller, right. So, if I start, it gets mapped to something smaller, right. On the other hand, if I look into this particular point, it gets mapped to something smaller and it goes to the other hand. So, if I look into a typical orbit of a point between 0 and 2, it basically shifts to the negative side to the left hand side of 0, then again goes back to the right hand side of 0. So, it oscillates about 0, and then finally, you can say that it basically is trying to converge to 0. What happens to the points which are greater than 2? So, the points which are basically the real numbers greater than 2, we will find that they also come up to something larger over here, right, on the other side, on the left hand side. And if I say take any point over here on the left hand side of -2, then that gets mapped to something which is larger and to the right of 2. So, the phase portrait of this function is very clear, where points greater than -2 and less than greater than 2 and less than -2, right, they are also oscillating about 0, but then their magnitude is increasing, their absolute value increases. So, typically here again, what is my stable set of 0? So, my stable set of 0 here is again -2 to stable set of 2 and stable set of -2 are again singletons. So, we are looking into what happens to the unstable set of 2. Now, I am looking into points which are drifting away from 2. What are those points here? And they are drifting away from 2 at the second iterate, right. So, at the first iterate the points come up here, at the second iterate they are again going towards the right hand side, right. So, at the second iterate I am looking into all the points which are drifting away from 2 at the second iterate, and we find the same story here, that this unstable set happens to be equal to 0 to union to infinity. And if I look into what happens to the unstable set of -2, again I have the same story. So, this becomes -2 0 union minus infinity -2. So, the unstable set of 2, the unstable set of -2, both the cases remain the same. So, we have this hyperbolic periodic point where the absolute value of the derivative at the period is not equal to 1. We will now go up to some proposition here. So, let us try to look into some proposition about a hyperbolic periodic point. What is basically the property of a hyperbolic periodic point? Why should we study them in that sense? So, if we have P to be a hyperbolic fixed point, right, I am just starting with a fixed point right now. So, if P happens to be a hyperbolic fixed point such that the modulus of f prime P is less than 1, then there exists an open neighborhood U of P such that for all points in this neighborhood, right, the limit, or basically for every x in this neighborhood, f n x, the orbit of x, is converging to P. In other words, we can say that we have an open neighborhood of P such that this open set is contained in the stable set of P. So, the proof here is quite simple. We start with the proof of this proposition. Now, all we have been given is that the absolute value of f prime P is less than 1. I can say that here so that means that for some positive delta I have a neighborhood of P such that the modulus of f prime of x is less than some quantity a, which is less than 1 for every x belongs to P minus delta, P plus delta. Now, I can use my mean value theorem. So, by mean value theorem, This is basically less than or equal to, right, a times mod of x minus p, right, because we will find something between x and p, right, and whatever we find between x and p, its derivative will be less than a, right, modulus will be less than a. So, we find that this is, by mean value theorem we can say that mod of f x minus p is less than a times mod of x minus p, and if I try to look into this repeatedly, right, we can say that since a is some quantity which is less than 1, right, repeatedly I can say that since a is less than 1, this particular part on the right hand side would be converging to 0, right, and hence f n of x can be said to be converging to p. So, f n x converges to p, and hence, well, whatever proposition says, we can take our neighborhood u to be equal to p minus delta, p plus delta. So, we have this open neighborhood around p such that u is contained in the stable set of p. So, all points in this interval are forward asymptotic to p, and hence there is an open set contained in the stable set of p. So, this is one of the properties for a hyperbolic fixed points that you can see, and that property says that if your modulus, if this modulus of f prime p is less than 1, then you have an open set contained in the stable set of p. Now, what does basically this give us, right? It is not very difficult to see that in case p is a periodic point of period n. So, if p is a periodic point, and I also want my p is hyperbolic, then some p minus delta, p plus delta, right, will be a subset of the stable set of p, provided n is the period of p, right, this is less than 1. So, if I have a hyperbolic periodic point such that the modulus of its derivative at f n is less than 1, then for such periodic points also the stable set happens to be containing an open set. With a little bit difficulty, we can try to look into, or we can try to analyze what happens in case I have such a periodic point and I have f n prime p is greater than 1. What happens in that particular case? So, if we again go back to our proof of the previous case, right. So, the previous case we had by mean value theorem, we had that this happens to be a quantity a which was less than 1, right. Now, if our f prime p is greater than 1, then I can say that I have an open set p minus delta, p plus delta, right, such that f n prime of x, right, this modulus is greater than some quantity a is greater than 1, right, for all now. What does this observation tell you? In that case, this particular interval will be contained in the unstable set of p, right. So, in this case, if for such a p, right, modulus of f n prime of p is greater than 1, then you have p minus delta, p plus delta to be contained in the unstable set of P. So, your hyperbolic periodic point, right, for a hyperbolic periodic point, if this modulus is greater than 1, then this becomes basically this is contained in the unstable set of P. We have a specific name or a specific property of such points. So, what happens now, again we are looking into hyperbolic periodic points. So, let P be a hyperbolic periodic point. Now, we have seen two cases, right. One case is if of course periodic point of period n. So, let me specify the period here also, period n. So, our first case is if mod of f n prime of P is less than 1, then what we find is that the nearby points, the points in the neighborhood of P are basically forward asymptotic to P, and in that case we say that P is an attracting periodic point. Attracting periodic point means all the nearby orbits are basically attracted towards P, right. So, all the nearby orbits they converge to P, and in that case we can say that P is a sink, or we say that P is a sink. Everything is, all the orbits are sinking towards P. So, we say that P is a sink. Supposing we have this case that f n prime P is greater than 1, then what happens in that case? It is greater than 1. So, what we find is that the neighborhood of P is basically in the unstable set. That means that all the points in the neighborhood are backward asymptotic to P. That means they are basically being moving away from P, they are repelled from P, right. So, in that case we say that P is a repelling periodic point, or we say that P is a source. Why do we say it is a source? Because everything moves away from there, right. So, it kind of works like a source. So, we say that P is a source. Now, we may come up to cases where P is neither a sink nor a source. That means, ideally when we have a periodic point which is neither a sink nor a source, in that case we say that the periodic point is unstable. So, we say that a periodic point which is neither a sink nor a source is called unstable. We never know what it is, what properties it may have. Maybe it is attracting something from one side, it is repelling something from the other side. So, for such periodic points we can't say anything. So, we say that they are unstable. So, these are unstable periodic points. Now, all we tried to look into is, we tried to look into the case when you have hyperbolic periodic points. So, you are looking into the case when you have hyperbolic periodic points, and now we are looking into what happens to the case of non-hyperbolic periodic points. So, before we get into non-hyperbolic periodic points, we just get into what we mean by a non-hyperbolic fixed point. So, we start with this definition. So, let P be a periodic point of period n such that I have mod of Fn prime p, right, this is equal to 1. Then P is called a non-hyperbolic periodic point. So, basically what we find here is that the derivative or basically the tangent at P, right, for Fn, the tangent of Fn at P, right, exactly happens to be parallel, right. So, this is 1 and hence we say that P is a non-hyperbolic periodic points. Cases of non-hyperbolic periodic points are much different from the cases of hyperbolic periodic points. So, let us try to analyze this case. So, we first look into non-hyperbolic fixed points and the rest of the things will be just similar. Now, if I look into non-hyperbolic fixed points, so non-hyperbolic fixed points will have two variety. One is when mod of f prime of p, so this is basically when mod of f prime of p is equal to 1 and this has two cases. I have that f prime of p is exactly 1 and the other case is that f prime of p happens to be equal to minus 1. So, we have these two cases. Now, we will try to look into the case when f prime of p happens to be equal to 1 and for that we look into a proposition. So, we start with the proposition here. So, let P be a fixed point such that I just want to emphasize here that mod of f prime p is 1. Now, we know that f, we have already assumed that f is continuously differentiable. Here I want to assume something more. So, if f prime, f double prime, f triple prime, these are all continuous at P, then we have essentially three cases. So, the first case says that if, now I already know my f prime of p is equal to 1. So, I am now looking into what happens to f double prime at p. So, if f double prime of p is not equal to 0, then my p is unstable. So, then p is unstable. Now, the second case comes up, what happens if f double prime p is equal to 0. So, if my f double prime p is equal to 0 and I have that f triple prime p is greater than 0. So, if I have these two cases, so f double prime p equal to 0 and f triple prime p is greater than 0, then p is a source. Now, we have a third case here which says what happens if your f double prime p is equal to 0 and your f triple prime p is less than 0. Supposing we have these two cases, then p is a sink. So, we have these three conditions for the fixed point, the non-hyperbolic fixed point p. So, for a non-hyperbolic fixed point, we have three cases. We are looking into the double derivative, we are looking into the triple derivative, right. So, the value of the double derivative and the value of the triple derivative gives us what is basically the nature of the fixed point. Now, I want you to look into this particular aspect. So, let me just draw a simple figure here. What do we mean by saying that f prime p is equal to 1? F prime p is equal to 1 means basically the tangent of the line or the slope of the line is 1 at that point. And on the other hand, we have that f double prime p is not equal to 0. Supposing I am looking into the case where f double prime p is not equal to 0, what happens in such a case? So, if I look into this case, the first case here, f double prime p is not equal to 0, then I have two cases, either it is greater than 0 or it is less than 0. So, if it is greater than 0, now if it is greater than 0, that means it is concave upwards, right. So, your graph happens to be something like this, there is a point P, right. So, this is basically your point P, right, and the graph is concave upwards. If f double prime p is less than 0, since it is not equal to 0, right, supposing this is less than 0, then we find that the graph of p would, the graph of f at p would look something like this. This is basically a p and your graph is concave downwards. Now, we try to analyze this factor, right, try to give a proof of this proposition. So, let us look into the proof here. So, we have two parts here, since f double prime of p is not equal to 0, let f double prime of p be greater than 0. Now, what happens, what is the meaning of saying that f double prime p is greater than 0? That means that at p, f prime p is increasing, right. So, f prime of x is basically increasing here. So, we find that, so for some delta positive, right, we find that f prime of x, because my f prime of p is 1, right, my f prime is increasing here in this interval. So, I find that f prime of x is greater than 1, right, in this interval p to p plus delta, and since my f prime is increasing and my f prime p is equal to 1, we find that f prime of x is less than 1, right, in this interval p minus delta to p. Is this clear to all of you? Okay. So, what we have here is, we have f prime x is greater than 1 in this context. What happens to any x in this interval? Any x here will be backward asymptotic to p, right. Any x in this interval p to p plus delta will be backward asymptotic to p, and since f prime x is less than 1, any x in this interval p minus delta to p will be forward asymptotic to p. So, basically p is basically attracting everything to its left, or basically some things to its left, right, and p is attracting something and it is repelling, it is basically repelling on its right, right. So, this p is can neither be a sink nor a source. So, my point p is unstable. If f double prime p is less than 0, so we are looking into basically the proof of the first part. So, if my f double prime p is less than 0, then definitely we find that, so it is a similar observation, we find that f prime of x, basically f prime is now decreasing, because f double prime is less than 0, f prime is decreasing. So, we find that f prime of x is less than 1, right, in p plus delta, and f prime x is greater than 1 in p minus delta p, which again implies, again it is the same story. So, this implies that p is unstable. So, non-hyperbolic fixed point such that its derivative at p takes the value 1, assumes the value 1, we find that f prime p not equal to 0 implies that p happens to be an unstable periodic point. What happens in the next case? So, we try to look into what happens in the next case. So, in the next case my f prime p, f double prime p is also equal to 0. Now, f double prime p is also equal to 0. What does essentially that mean? So, that means that we are now looking into the third derivative, and my second case says that this is 0 and the third derivative is greater than 0. What happens in this case? So, we find that in this particular case your f triple prime p is greater than 0. Since this is greater than 0, that means your f double prime p is increasing, right. Your f double prime p is increasing. What does that imply? It is greater than 0 in p plus delta, p plus delta, it is greater than 0, and it is less than 0 in p minus delta, p plus delta. So, what happens in that case? Your f double prime p is less than 0, right. Now, I am again coming back to the previous case, it is less than 0 in this interval, f double prime p is greater than 0 in this interval, right, less than 0 in this interval. What does it imply? Right, it implies that your f prime p happens to be greater than 1 in both these intervals, right. So, in both these intervals p plus delta and p minus delta p, your f prime of x is greater than 1, right. So, this implies that f prime of x is greater than 1 in both say p plus delta and p minus delta p. Since this is greater than 1, right, we can easily use our previous theory or basically our previous observation to say that in that particular case p is a source. If I look into my third case, what happens into my third case? So, in the third case again I have f double prime p is 0 and f triple prime p is less than 0. Now, f triple prime p is less than 0 will give you that f double prime p is decreasing basically, right. It is decreasing in the neighborhood of p. Since it is decreasing in the neighborhood of p, which means that your f double prime p happens to be less than 0 in p minus delta, is less than 0 in p plus delta, and is greater than 0 in p minus delta p. In both cases that would mean that my f prime x will be less than 1, right, in both these intervals. So, my p here is a sink. So, for a non-hyperbolic fixed point for which your derivative, the value of the derivative is 1, right, we find that this is it's either unstable or it is a source or it is a sink. What happens for a periodic point? Again, the calculations would be a little bit, I mean our computations would be a little bit turdy, but we can say that here that for a periodic point, a non-hyperbolic periodic point also, we get similar cases, right. So, they will be either unstable or they will be a source or they will be a sink. Now, my basic interest is looking into what happens for a non-hyperbolic fixed point where f prime of p happens to be equal to minus 1. So, if I look into that case, then we have here for that we need to look into some other concept here, and that concept basically is the concept of Scaasian derivative. So, what do we mean by a Scaasian derivative? So, we defined a Scaasian derivative of a function f to be equal to f triple prime of x divided by f prime x minus 3 by 2 f double prime of x divided by f prime x whole square. Now, this is basically the Scaasian derivative for any function defined on the interval, such that of course, f triple prime is defined and f prime is not equal to 0 at any of the points. Now, if I try to look into what happens in the case of a non-hyperbolic point, where my f prime p happens to be equal to minus 1. So, you have a non-hyperbolic fixed point such that f prime p is minus 1. In that case, I simply can deduce that my Scaasian derivative at p is minus of f triple prime p minus 3 by 2 f double prime p whole square. And we can now try to analyze this, because this analysis comes up in terms of Scaasian derivative. So, we have a proposition here. If I have p to be a fixed point of p with f prime p taking the value minus 1, then and again if my f prime, f double prime, f triple prime are continuous at p, then this Scaasian derivative is negative, then p is a sink, and if the Scaasian derivative is positive, then p happens to be source. And this we will not look into the proof of this, maybe I leave the proof of this to you. This is easily proved taking this function g equal to f composite f. When I take g to be equal to f composite f, whatever is the nature of p for f, right, the nature of p for g is same as the nature of p for f. So, they both have the same, p has the same nature under both these functions, but the advantage here is that g prime of p will take the value 1, and hence we can use the previous proposition, but I leave this as a homework, right. So, one can see that we have Scaasian derivative to analyze what happens to a point p when it is unstable. Maybe we stop today, we stop here.